Good morning, everyone, and welcome to Big Data Today. Last week, we studied MapReduce. We looked at the CAP theorem, which has implications on every distributed system. And we saw that what implications the CAP theorem on ACID, for example, would have in a distributed system. And then we looked into this NoSQL world, and in particular discussed Bayes, which is a set of properties in distributed systems that is often used in a lot of settings. It's something quite different to ACID and has its own pros and cons. We also saw how we can speed up training when we have large data sets using GPUs, but also FPGAs, for example. Discussed a little bit how FPGAs work and how you can configure them. Then we started looking into the next chapter, discussed data quality and some issues. And those of you who do the AI project with me in parallel, you see all these data quality issues in the real data sets you get from our industrial partners. And we started also looking into the term bias, and we saw a bias may mean a lot of different things in the machine learning literature, like the inductive bias could be a synonym also for underfitting, or this y-intercept parameter in a lot of models. But none of that is what we are referring to now. We are interested in situations when the distributions of the training and data, when the distributions of the training and test sets are different. We saw biases not only appear in AI, but generally in statistics when you collect data. We saw this example from 1936, how a heavily biased data set actually led to wrong predictions. Some people pinged me, they have questions on the seminar part. I'll say more about the seminar anyway at the end of today's lecture, and then we'll see if there are any questions left. So we looked at this bias example, and we said we have a bias when the distributions of the training and test set are different. The actual sets are different, that's fine. If your training and your test set are different, that's actually what you want, because you want to predict and test on unseen examples. But we always assume that these two data sets come from similar distributions. Now, in reality, that's often not the case, because somehow we collect our training data and then we apply this model to users that may not fit into the original distribution. And that leads to a bias. And we can also mathematically define what a bias is. We can say, well, we have our data. So this is now from a supervised setting. We can say we have p-train where x and y are bold, because this refers to the probability distribution of the training set. And x refers to the input and y to the labels. And if these two distributions are different, then we have a bias. Now the question is, we can measure bias, and then we can try to actually correct for the bias. Did any of you ever deal, maybe in your internship or in some project, with biased data sets? Okay, what did you work on?
Some on the layers, like images of cells, also in the project of machine learning, different body giving, and some of these matches have like, we're all layers, like they have like data like incredibly not common.
Okay. And how did you fix that issue? Okay, so you chopped out. Okay, fine. One solution. I saw another hand raised. I think you raised your hand.
Sure that it's retracted, but it was a heavy biased data set. I think it was optimized driving.
Okay.
traffic lights and the reflections of like security vests, they interfere to me. So I also normalized them and had some data augmentation.
Okay. So both problems that were described are from computer vision, and the students augmented the data or chopped off some data or normalized. So we will see this now from a very abstract perspective, and we see these two distributions are different. In reality, that's always the case. You will hardly have exactly the same distributions, but we can maybe try to minimize the bias. And the literature proposes the following. So we can do, for example, weighting. We could see when we have a training example, how important it actually is when we train a model. But for that, we also need to know what the test distribution looks like, or we could try to estimate it. That's maybe something we not always have available because we just don't know who would use that model, but it's a beginning. So if we can make some inference about our test distribution, and we have our training data, and we know then the distribution of this training set, we can weight examples, and we can say the weight of our example I is the probability of the pair of the input and the label appearing in the test set divided by the probability of that appearing in the training set. This is something that was proposed in the literature maybe some 10 or 15 years ago. And notation here is important. X is in bold because could be multiple dimensions in the input, and we have a corresponding label. And if we calculate these probabilities and divide them, this could allow us to have a weight and at the training phase say how important that example is when we do the training. However, for this, we need to know something about, or at least estimate where our test data would come from in terms of the probability distribution. This works if we can estimate p-test, but it leads to some new consequences if we try to calculate it this way. Have you ever seen some machine learning model or some library where you can pass some weights for the training, not the weights of the model, but the weighting per example? Have you seen this ever? In some models in scikit-learn, you can pass, when you pass your training data, you can also pass a weight vector for each example that would be that weight. Has any one of you ever seen this in scikit-learn? Can look it up. Not all models in scikit-learn offer this, but some. And this is exactly meant for examples like this, where you can say how important the actual examples would be. But here comes a challenge. Calculating these probabilities is very difficult. Any guess why this could be very difficult to calculate? Because X is a vector and could be potentially very large. So I could be dealing here with a high dimensional problem, and I don't have like, an analytical solution of these probability distributions. Rather, I need to estimate these densities from my limited set of examples. So that's challenging, because what we need to do is we need to estimate a potentially high dimensional probability distribution, which is actually a joint probability distribution because it's a joint of X and Y. But X, again, can be many, many dimensions because it's a vector. So estimating this could be extremely slow. And because of the curse of dimensionality, this could lead to a very, very uncertain estimate. So it works theoretically, but in practice, it does not work very well because we always have we have a limited set of examples, and we suffer from the curse of dimensionality. We can, however, try to make some discretion about this bias, so we can make some assumptions, because this is just in general a bias. But now we could say, rather than that bias, we could come up with specific biases. We could make some assumptions. And one of them is class imbalance. Probably, who of you has dealt with class imbalance when training models? More, but you didn't call it a bias, because you just call it in the literature class imbalance. It turns out class imbalance is just a specific bias. Class imbalance means we have an unequal amount of examples per class when training the model. And what happens if you have the situation when one class is much more overrepresented than the other? So some of you raised their hand and said, you have worked on class imbalance. What happens when you train a model on a data set in which one class is much more represented than the other? Yeah? The model tries to predict that class more. Sometimes that's needed. Sometimes for some problems, that's simply the reality. And sometimes you need such a bias because it's simply the reality. And sometimes, and we got the same here in the chat, there's a high chance of predicting that maturity class. But sometimes maybe you want to get rid of that bias and have a more unbiased model. So using our framework from before, because one challenge here was this joint probability distribution of X and Y. We can say for the class imbalance that the distribution of labels is different for the training and test set. We can say those are different, but we can say we can introduce now a conditional probability distribution for the training and the test set of the data given the label, so X given Y. And if these two, and we assume that these two conditional probability distributions are the same. And this can lead to some very interesting situation. And this is just one example of class imbalance, where one label is represented far more than the other label. And now, why do we introduce this second line? It will help us very, very quickly with something, because we say the distribution of the labels is different, but this conditional probability distribution of X given Y is the same for training and test. Because we can plug this in our weighting scheme from before. Because this was what we said before, that we tried to weight this by taking the probability of that pair appearing in the test distribution divided by the probability of this appearing in the training distribution. We said estimating this is so difficult. And now we can always break up a joint probability into a conditional probability and a prior. Who remembers this from the statistics class? Not that many. You should maybe revise. But this is also, I don't know what Bayes rule is based on. You have a joint probability and you break it up into a conditional and a prior. Rings a bell, right? And I can do that here. I can break this joint of X and Y into X given Y times this prior, so the probability of P test given the label. And I can break this up not just for test, but also for training. So rather than saying P of train of X and Y, it's X given Y times the prior of Y. But in the page before, we said that these conditional distributions, we said before the conditional distributions, and here it's now the conditional probabilities, because it's for a concrete example, we say they were the same. So we can just cross them out, because this is just the one thing divided by the same thing, which is 1. So we cross it out. And eventually I can say this is P test of Y times P train of Y. So I have severely simplified this weighting problem from before, because I'm only dealing with the labels. And now I have calculated these weights very reliably. How do I know that there is actually a class imbalance in my data set? because we have now made a very strong assumption. We said we don't want to solve a bias in general, but rather some specific bias. This is something you would figure out from an exploratory data analysis early on. And then you see, well, I have a class imbalance, maybe something to correct for. And now you can use these weights when you train the model, but you could also prepare your training set in a different way. You could do some undersampling or oversampling in your training set. So undersampling means you would reduce the majority class, you would sample this less often than the minority class. If you oversample, you would pick the examples of the minority class more often, and you would increase the set. So you can do undersampling or oversampling as an alternative. The sampling would also happen eventually, would be related to this weight, but you would pre-process your training set. Well, here you pass the weight in the first approach into your machine learning model. There is also other stuff, like the literature for a long time has been proposing a method like smoothie, which is the synthetic minority oversampling technique. Essentially, it combines over and undersampling. But in recent years, this one here has received more criticism. Some people claim smoothie doesn't work at all, that it's only something that worked in research paper, but doesn't work too well in reality. I disagree with this. I have seen good examples where smoothie actually works well, but some people have been very negative about it. It's just, to present you with alternatives, what you could try out to reduce your bias. But this is in fact a very simple bias, a class imbalance. But it turns out in your data, there can be totally different biases. One that is very common is a covariate shift. And in a covariate shift, we make different assumptions. There was one question on smoothie. Well, what smoothie does is, if for the minority class, it tries to build synthetic examples and upsamples or oversamples this minority class with synthetic examples, and then the second step downsamples all of this, but also making this assumption of how to build augmented examples from the minority class. That's a bit uncertain, and that's why smoothie gets now more and more criticism. But the other bias is covariate shift, and covariate shift is something that is much more tricky to find in your data than the class imbalance. And in fact, it appears very often. Covariate shift, for this we make two assumptions. We say the probability of the input data X in the training distribution is different to that in the test distribution. And in order to take advantage of our rule that we can break up this joint probability, we now say we have these conditional probability distributions of Y given X are the same for the training and test distributions. This is what a covariate shift could look like in 2D. So I don't have labels here because we see the labels don't matter because this is the same, but we see they have a 2D data set, and for the training, this data set is totally differently distributed than for the test set. And this would be an example of a covariate shift. And this is something more tricky to find because this is an easy example in 2D, could be in ND, and then it becomes more tricky. But we'll later see how it can be measured. And we can just apply this as before. We use our weighting, and this time we break this up in a different way. So we say X and Y is Y given X times X. It's just the other way around as before, because before we said X given Y times the prior of Y. But this can also be done this way. And then we assumed that the test distribution is the same as the training distribution for the conditional Y given X. So these two are the same. We can just cross them out. And now we have simplified this problem to a probability distribution to probability distributions that we need to estimate purely for the data and not the labels. This is still more challenging than for the class imbalance because X is now still a vector, and this one here may still be high dimensional, and this one as well. So correcting for this covariate shift in high dimensions is more difficult than for your class imbalance. You can use this weighting. Some people also use rejection sampling when they pre-process or prepare their training set. I worked a lot on this kind of stuff in my PhD thesis, and I also proposed some method how to calculate or how to estimate this one here more efficiently, because it could still be high dimensional, and we could still suffer here from the curse of dimensionality. Now, how does this appear in reality? It actually appears very often in reality. And when we started with this course, like 4 or 5 weeks ago, I also talked about the manipulation of power infrastructure as one use case that I worked on and how to reduce it. When I started with my PhD thesis, I was not really much aware about this bias thing. I knew class imbalance, but all the other bias stuff, I didn't see this before. Even though I did a whole master's in machine learning, no one there really talked about biases in data sets. So what I did early in my PhD, I built a model aimed to predict who steals, and noticed it worked okay, but it didn't work as okay or not as good as I expected. And then I dig deeper and learned about this issue of biases. And I saw this data set was heavily biased. I'll start with a quick example to show you where this could happen in reality. So my machine learning model to predict the electricity theft, so per customer who actually steals, was based on the idea that some of the customers get inspected by technicians and they either report fraud or no fraud. And we have all this other customer data like meter readings and where the customer lives, the meter type and so forth. And from that, we built a model to predict the label for all the remaining customers. But it's biased. And I'll quickly show you how a bias can already appear in your data set. Imagine for now, we have only one state in Brazil. And it's not, by the way, the state where I got the data from, because the technical partner did not want to disclose from which state we actually got the data to avoid any kind of political influence or whatever. So it's just some state in Brazil. And what we have are 2 cities now, just as a simple example. We have a very big city, which is this big circle, and a small city, which is this circle. And I have, say, I can carry out 1,000 inspections. I have resources for this. But maybe most of my technicians are in the small city that I have free, and just a few technicians are in the big city. So this big magnifying glass means I carry out most inspections in the small city and a small part of the inspections in the big city. This already leads to a big bias in the data set, because maybe the electricity consumption behavior in the big city is totally different to the small city. In particular here, this is in Brazil, so it may be very hot in the summer at the coast, so people need more aircon than the ones who live more inside the country. They may still need aircon, but maybe less. But I got most of my samples from the inspection from the small city and not the big city. What I have here is a spatial bias, but this is just one of many other biases that can appear in that setting. And in reality, it's not just 2 cities, it's a lot of cities. Maybe some types of meters get more inspected than others. Maybe some meters are easier to inspect than others. All of this leads to a high dimensional bias. And then I proposed some methodology how to measure this bias with a lot of covariate shift effect, and then how to reduce it. And one part of my PhD thesis was about this. And what I wrote during my PhD time was also a survey paper about the impact of biases in big data. This paper, you find it on the net. I think I also put it in the Nextcloud directory. It's just for you if you want to learn more about biases. We did a survey about that time about what was available in the literature. It's now 7 years old, but the field has actually not progressed much because not a lot of machine learning people actually work on biases from a research perspective. Feel free to read the survey paper. I think it's like 10 pages or something. If you want to see some more examples of biases, how to measure them, and how to maybe debias. And my PhD thesis offers some more advice on work that was done later. There's obviously a lot of negative news about biased machine learning models, like machine learning models that discriminate against certain genders, against certain parts of society. And I see a lot of criticism about that. And yes, criticism is important, but when I see some NGOs, like, for example, Algorithm Watch, they run around at conferences and claim, biased models, biased algorithms would end the world and we all would die. And you talk to these people, it turns out they actually don't know what a bias in machine learning is. So there's maybe a good intention to reduce the impact of this. But if you run around at conferences and warn everyone that the algorithms would end the world, you should at least maybe study some of the fundamentals. But you're studying AI, so feel free to read the paper, could provide you with some insights about what biases are. And machine learning models don't become racist on their own. They may exhibit this behavior because of training data, and that training data comes from humans. So sometimes maybe biased machine learning models can even, help us to reflect on our own behavior, about the mistakes we have made. And then machine learning models learn them too. It turns out, so this is the covariate shift that we talked a lot now. There's even something that is called internal covariate shift. An internal covariate shift happens within a neural network if you don't pay attention to it when you train it. And then maybe you have data that does not have much covariate shift, but the neural network learns a internal covariate shift on its own. This is, it doesn't lead to discriminative or to negative behavior, but it leads to overfitting, in fact. And this is something that was noticed maybe some 10 years ago in the literature, that internal covariate shift can happen in a neural network. And what it means is that you have, when you learn layer by layer, you actually learn sort of a bias from one layer to the next one. And there's various methodology to reduce that internal covariate shift. And when you address this, then your neural network overfits less. This is something that was, as I said, reported about 10 years ago or something like this in the literature, and practitioners are now aware of it. This whole field of big data is a bit strange to me from the news perspective. So what I see is there's a very famous machine learning researcher in California, Michael Jordan. He was so he's not the athlete. He was always very critical about big data, because a lot of people promised, I remember this 10 or 15 years ago, you only need ever bigger data sets and you can learn whatever you want and you don't need to understand anything, you would just learn this. He was very negative about it, and maybe too negative even, but he said some good stuff in the interview some years ago that appeared in the IEEE Spectrum. And I share some of that criticism, but I noticed something, that people in Silicon Valley and others around the world that propagated 10 years ago big data and claimed you only need big data and then we can learn whatever we want and we don't need to do anything else. They noticed it failed. And now they are running around just saying, oh, now we need small data, and they still get funding. They failed with the stuff they promised 10 years ago. And now they promise the same stuff, just about the opposite. And small data is helpful, but neither small nor big data are the solution. What you need is better data and more representative data less biased data, and that helps. But feel free to read that interview if you wish. Now, as we talked about big data, sometimes big data can also mean we have very large examples like CT images, but maybe just a few of them. And then we run into so-called small sample size problems. And small sample size problems addresses the number of examples that is small, but the examples may still be limited. And this are big examples, but limited amount of them. And this is something we deal with like in CT images and some other biometric data, for example. And for this, we need to build models in a different way that they work. Because so far, we have always assumed we have a big amount of data for training our models. What is now if we have a small amount of examples? Yet the examples could be big, could be small, but we have a limited amount of them. What typically happens when you train machine learning models with a small amount of data? When you have tried this, what could be some outcomes, positive or negative outcomes? And why they don't work? Okay, so they could overfit. Is that what you mean? Okay, so they don't generalize. One advantage could be maybe the training goes very quick, but maybe the model does not generalize. So I've said this, we have, this could happen in biometric identification, CT scans, and so forth. And yes, we could have poor results, maybe overfitting, but it turns out that some machine learning models are even not trainable at all if we have a data set that is too small. Mathematically, they're not trainable. This is something that happens with certain settings. And we'll look at a simple example to see this now. Linear regression, something you're all familiar with. We have M training examples and they have N features. So my notation is always M for training data, examples and N for the features. Some people, they just swap them, but I prefer this notation. And this is what linear regression could look like. We have a housing price estimation and we have the input, the size, and we want to predict the house price. And we can make this more complex by adding more features, because here we just have one feature in the input. And our hypothesis looks something like this. So once I have trained my model, I have my weight vector, and the hypothesis I put in an example X, and I want to predict what its output is. And from a purely linear algebra perspective, I can just say I want the dot product of the weight vector and X. The dot product is one thing, or scalar product, whatever you call it. But I can also see this as a multiplication. So I have both vectors are column vectors. So X is my column vector. And I can also transpose the weight vector from a column vector to a row vector. And then I multiply them, and eventually I get a scalar value. And what I'm doing is I say weight 0 times x0 plus weight 1 times x1, and so forth, up to weight n times xn. So the nth element. And because I need this W0 as a y-intercept, my convention is my x0 is 1. So this is something we have all seen in a machine learning class. And this is one example what I could do. So I have two weights just for this housing price example from before. And my size is 1,500, I think was square feet or something. And this one here is just a 1 by convention that I can simply write this out as a multiplication of a weight vector and the input. And eventually, this is just a linear algebra view on this. And I get 594. Now, quick summary or quick reminder from your side. How do I train a linear regression model? What is the approach to find the weight vector? What was the approach that you learned in your machine learning course? Yeah. Exactly. And how do I find these weights? Yes. And what's the name of that method to reduce the error? Well, the mean square is the error, how I calculate the error, but I want to reduce the error. Yeah, exactly. Gradient descent. So what you just mentioned is my cost function, the error function. And one way I can define this is just I take the predicted value from the hypothesis minus the ground truth. I square the error. I sum all the errors together and I divide this by m or 2m. There's a convention if I divide it by m or 2m. I could also just leave the sum as is, but the sum will just get very, very large. And like this, I normalize. And I optimize the weight vector by doing gradient descent. What's an advantage, or what's maybe a disadvantage of gradient descent? Yes, but not in linear regression. If I use the cost function, the squared error one, for a class for in linear regression for regressing, then it's a convex problem. So I cannot get stuck in a local minimum. But still, what could be an issue? Maybe convergence could be an issue. How quickly do I get to the minimum? I need to set the learning rate, and maybe it overshoots. For a neural network, we just had a small issue with the projector. Can the ones on Zoom confirm if you still see the slides well? Because our projector just turned off for a second. And from my experience, the slides are not shown very well anymore after this. But we got confirmed the slides look fine. And with a neural network, I may have local optima, which is not great at all. So ideally, for these methods, it could be interesting to have an analytical solution. For a neural network, this does not exist. But for linear regression, it turns out there is an analytical solution. It's called the normal equation. Has any one of you ever worked with this? Because we'll discuss it now and then see how a small sample size problem could appear. So gradient descent is nice, but we said, well, I need to find a learning rate and it needs to converge, and maybe it converges very slow because I need to do lots of stuff. And this would be the gradient descent. What I'm doing is I have a loop until convergence and I optimize each weight. So here weight j by subtracting the partial derivative. And it turns out this is the partial derivative for weight wj when I have the squared error cost function from before. It's something you see in your machine learning course, how to find these partial derivatives. So we assume this here. But you could just see this is the partial derivative. And I do this in parallel for all the weights, and I stop once the loop has converged. But how quickly does it converge? I need to find the learning rate. All of this is challenging. And I need to pre-process the data. I typically need to do some scaling on the data. Otherwise, convergence is slow. And with the normal equation, it turns out I have an analytical solution to linear regression. The analytical solution is, so X is my input matrix. So just for the convention, the rows in this matrix are my inputs. And so the columns are the features, and each row is one of my training examples. That's X. And if I transpose X and I multiply this with X, and I take the inverse of that product, and I multiply this with X transposed, and then with my vector Y, so it's the vector of all the labels, then I get an analytical solution for my weight vector in linear regression. Has any one of you ever seen this equation here? It's an analytical solution. So I don't need a learning rate, no loop, no feature normalization. And that means you can implement linear regression in one line of code when you use some library like NumPy or whatever. Just a few statements. You can write this in one line of code. Why does this work? You can derive the normal equation, and it turns out this works okay. It gives us an analytical solution, but it can become quite slow for very large matrices, because the complexity of the inversion, at least so multiplying two matrices is O of n squared, but the inversion of the matrix is O of n to the third. When you use some better algorithm for inversion, does anyone remember, because I remember almost all of you from my algorithms and data structures course, who remembers the Strassen algorithm? Oh, and sorry, I made a mistake. Multiplying them is obviously not n squared. It's O of n third as well, because adding the matrices would be squared. So multiplying is O of n to the third. The Strassen algorithm provides a small speed up. So n to the power of 2.7 or something. It's used for multiplying the matrices, but originally when the Strassen algorithm was proposed, it was actually proposed for matrix inversion. It's a consequence of the Strassen algorithm. So instead of n to the third, we can say n to the 2.7, but still it could be a bit slow. But the normal equation is still interesting, and if the matrices are not too big, it actually works quite well and gives us an analytical solution. Where does this come from? Deriving this is complex because you need to study a combination of calculus and linear algebra to come up with the normal equation. One person said the screen share doesn't work now. So that's fine, because that's what I warned about. Maybe you can confirm that the screen share works now. Deriving this is complex. There is stuff like the matrix cookbook that would show you how to derive this, but it's challenging. I just have an intuition. Very importantly, this is not a derivation. It's just an intuition of where the normal equation may come from. For a classic prediction task from a linear algebra perspective, I have X, which are rows of examples, and I have my weight vector, and I can multiply the weight vector from the right with X. So eventually the weight vector will be applied to every row. So for each row will turn into a scalar. And this is how I get my vector Y, which are all my labels. This is just, the first line is just classic linear algebra from an introduction to machine learning. But now I can try something. I can multiply on both sides of the equation X transpose here and X transpose there. Now I could try on both sides to multiply both sides with X transpose X and the inverse of this. So I multiply this here and multiply this there. And what we see then, we have X transpose X and the inverse of this. And here we have X transpose X, exactly in the right order. So this actually neutralizes itself, and we get the identity matrix. Because something inversed times something just leads to the identity matrix. So we could say the weight vector is just this, what I had written up there. But it turns out, this is super important, this is not a derivation, it's just an intuition. The derivation will take a few pages of very complex vector calculus. So this is something can be shown in the literature. This is interesting, but the only thing that concerns me is the inversion. Because inverting a matrix is not that easy, and some matrices cannot be inverted. So what I can say is I have this product X transpose X from before, which I want to invert, but it could happen that I cannot invert it. And I cannot invert it, for example, if I don't have enough features. Sorry, if I don't have enough examples. So I have too many features, so I have more columns than rows. So M would be less than N. Less examples than columns. Now, I've said before, this could be a big data problem in the sense where I have a limited amount of examples, but super long rows. So I have a lot of columns in there. Maybe 100,000 features and just 100 examples. Then this one here will lead to a matrix that is singular that cannot be inverted. There's other stuff that can happen while the matrix is singular. Maybe you have redundant features. So if you have two columns that are just the same, if you have two columns that are linearly dependent, maybe just the same columns, or maybe you would have the size of a house in feet and the other column would be the size of the house in meters, then they would also be linearly dependent. And if you have two redundant features like linearly dependent features, then the matrix will also become singular or non-invertible. What can we do to reduce or to solve this? We could just delete a lot of features. We could add a lot of examples if we don't have enough examples. But if we have redundant features, probably delete some features. We could, instead of using the inverse, we could calculate the pseudo-inverse. Anyone has ever heard about the pseudo-inverse? Something you find in a lot of linear algebra libraries, often called p-inf, like the inv-inf is typically the inversion function or method. And the p-inf is the pseudo-inverse. What does the pseudo-inverse do? This is a huge theory that alone would probably take 2 or 3 lectures to discuss how the pseudo-inverse works, but it's something you may see in an advanced linear algebra course. The pseudo-inverse returns us the inverse of a matrix that cannot be inverted by making some assumptions. It's the Moore-Penrose pseudo-inverse. So those who came up with it, they also got some Nobel Prize or some other award, something that was proposed maybe some 50 or 60 years ago. It's a masterpiece in linear algebra. So rather than, inverse, we can just say pseudo-inverse and it's solved. This is one approach, but maybe gives us a poor estimate of the inverse. We can also try to regularize our expression from before. So we could regularize this piece here and add some or regularize it in a way so it becomes invertible. And it turns out you can do the following. We're just adding something on top. So the challenge was I have X transpose X, which I may not necessarily be able to invert. And I multiply this with X transpose and Y. So these multiplications are not critical. The challenge is the inversion. And I can regularize it by adding a matrix on top that has only ones in the diagonals, all zeros, but the first element is a 0. Why don't we use just ones? Why do we put a 0 in the first element? Any clue? Do you remember what the first weight stands for in our weight vector? The first weight in the weight vector is our y-intercept. And that's why we said the x0, so the first feature is always 1. That's what we saw before, so we could come up with this linear algebra expression. And these ones are not a problem, and I don't want to change them because this would severely impact the y-intercept, so I leave this just to a 0, but for all the other features, I add a 1 on top. And I put this in the diagonal, and I sum this on top of X transpose X, and I have a hyperparameter, lambda, which must be greater than 0. Oftentimes, you would use a small lambda, and you would sum this on top of X transpose X. And because you're adding a 1 on the first feature or on the first column, then the other, this is how you are actually removing this linear dependence of features that we saw before. And this also solves this if we don't have enough training examples. You can try this out with a small data set on your own, where you have an X and you come up with X transpose and multiply X transpose with X. And then you see what the output matrix would be. And you will see that there may be some linear dependencies in there, depending on your data. But if you add this on top, it will disappear. So by using this regularization, we have solved the small sample size problem, because the small sample size problem was here. We don't have enough examples to actually make this work. And it turns out this approach not only applies to linear regression, but there's a whole family of machine learning models, like, for example, LDA, the linear discriminant analysis. A lot of them are based in one step on something like this, X transpose X. And if you don't have enough examples, this will not eventually work if you try to invert it. So we're adding something on top. So this can be applied to more than linear regression, but actually to a whole family of machine learning models. Because small sample size problems are an issue. I don't know, it's the same if you do PCA, the principal component analysis. If you have more examples than features, fine. But if you have more features than examples, your principal component analysis will also not work, and you need to do a trick. So this not only here appears for linear regression, but many other models. And some of them, not the PCA, but some of them can be solved with this regularization approach. For the PCA, there's a different approach. When I studied machine learning in one of the courses, which was called Advanced Data Analysis, the professor spent 1 week only on different regularization approaches for this problem. And because you can do more, you could use random values, you could use some other matrices in here or some other. There's 1 week of lecture, just how this one here could be influenced. Not relevant for today, I just wanted to show the essence. But if you ever run into such an issue where you have an X transpose X, and as I said, it happens in quite a whole family of machine learning models for small sample size problems, you can regularize like this. You need to find a reasonable lambda, typically a small lambda, not too huge, and plug it in, and then you get something that can be inverted. It's an approximation then. It's not the absolutely correct result anymore, and that's why there are other possible solutions. So we have done our small sample size problems, and there were a few students, they had some questions on the seminar, and I'll talk about this now. I had sent you a round message in iLearn. We can just look at it together. What we saw is you can pick your seminar topic between April the 23rd and 30th, so it will open next week. And there are numerous topics you can pick. It's important, you need to be a group of 3 to 4 students. And we have all these patterns 1 to 30 from the Machine Learning Design Patterns book. Or we have selected chapters or selected subchapters from the Mining of Massive Datasets book. And concretely, these are the topics here. For example, some extensions to MapReduce or PageRank, how to calculate PageRank efficiently on large data sets. Also, I don't know, things like the singular value decomposition. So there's quite a lot for you to pick. If you like machine learning design patterns, the book is fine. Otherwise, the other book. And you can pick your topic between April 23rd and 30th, and it works the following way. We have down here this presentation topic entry in iLearn, and you would just click on which topic you would, which group you would join. Make sure your other group members are also joining this. It's always 3 to 4, not 2, not 1, not 5. So you need to find group members. And once you have found your group and your final, please edit the group description. This can be done by those group members, and add also your names again and your student IDs, because I only see your names in the iLearn group, but I don't know your student ID, and I need this to enter your mark. So you would just update this group here and put in all the names, and so that not just the student IDs, because I need to know who is who, but you would put this in this group description, so the combination for each group member. And all the topics here are available to be picked next week. And I will also say a few words about the marking, and then we'll see if there are any questions left. So this is the one book. It's available as an ebook through our library. This book, we have some hard copies in the library, but you also find it for free, the preprint for free on the website of the authors. If you don't want to buy the book, we were not able to buy the ebook because the ebook costs something like a few €1,000 for the university, because I asked them to order the ebook and they said it's too expensive with that publisher. This one here was fine, but this one we weren't able to procure. So they ordered a few hard copies, which is cheaper. Plus the preprint is available on the author's website. We're unable to spend a few €1,000 on the ebook. So that's why here I wrote originally early May. Now it's end of April because we're a bit faster. And you will prepare the seminar presentation. You as a group of 3 to 4 will present for 15 minutes. It's a weekend in June that I also announced. You know when it is. Concretely, this is, just that we're on the same page, it's June 21 and June 22. I'm unable to accommodate who can present on Saturday and Sunday. I just need to see how the topics are picked and that they build on top of each other. Probably I will aim to do all the design patterns on one day and all the other things on the other day, but I just need to see how many topics get picked. And we will have these seminar presentations on campus and on campus only, because I want your grandma to survive the big data seminar. And after your presentation, we'll have a 5-minute Q&A session, which will not just be about your presentation, also about the content of the lecture. I will not ask you to enumerate random stuff, but maybe just some questions to see if you have attended a course and understood the lecture stuff. And there's also a marking template, so you can score up to 50 points and 10 for the Q&A. And if you pick one of the machine learning design patterns, initially you should present why or the issue that the machine learning pattern addresses. So the motivation and the problem, then your design pattern and why it works, a little bit of code to see how it works. The book also, each book chapter presents alternatives to that design pattern. You should discuss some of these alternatives, and your slides should look reasonable. You don't need a professional designer, but if it's just black and white and you have thousands of words on one slide, doesn't look very nice. So, and in total, you can get 50 points. And for if you do the mining of massive data sets, there's a slightly different marking template. There's also a Q&A session and a visualization as before. The motivation and the problem would be a little bit shorter than in the book for the design patterns, but the problem is also described in detail in this mining of massive data sets book. Depending on the algorithm that you present, we may need some preliminaries. So if you pick something like, I don't know, singular value decomposition, you may need to just briefly present the relevant preliminaries that we need to understand this, but just the essence, just quick. Then you would present the actual algorithm that the book presents, a little bit of code to show us how it can also be run and how it works, and then your visualization. So it's a slightly different marking scheme, but you can also get up to 50 points because the machine learning design patterns are quite different to the stuff in the book on mining massive data sets. So we need a somewhat different marking scheme. But none of this is more difficult than the other. It's just two totally different things. So I need to do this. And then your mark will be turned, or your score will be turned into a mark with the usual table that I use in all my courses. 50 points will be a 1.0, 49 points will be a 1.1, but because that mark does not exist, it always gets converted to your advantage. And this is the mark you get in the big data course, and you will get a different mark in the deep learning course by Professor Wahl in case you take it. But we also have some exchange students who don't take Professor Wahl's course and only mine. And it's also a few things. You need to give the presentation in both courses this term. You cannot just present with Professor Wahl this term and next term with me. You need to do both presentations and pass both of them in the same term. And because it is a seminar style, there will also not be a resit in the winter. So you need to do it this term, because if just one person gives a presentation, we don't have a seminar. So a resit doesn't make much sense in the winter. And this is the last time I'm teaching the course. Next year, someone else will teach it because I have too many courses. So, and then there will be new content and new presentations, or maybe even no presentation, something totally different, because we've hired a new AI professor and she's looking forward to starting to work here in autumn. And I have just too many courses and I'm just very grateful I can move one course to her, even though I like this course a lot. So that's why I finished this stuff this term, because next year everything will be totally different and you would need to start from scratch. Are there any questions about the seminar so far? Because you said before you have some questions. For everyone in the group, most of the questions may be about the presentation, but maybe there could be something about the course as well, because I notice every year less people actually follow the recordings and don't attend the lectures, just hope to take the presentation. But the presentation only makes sense if you have seen all the other stuff in the course. Okay, so it's not 50 minutes of presentation, then 5 minutes per person. No, for the whole group. And yeah, so we need about 20 minutes per group. Any other questions? Yes? I aim that everyone in the group gets the same mark. However, if I see that one person doesn't present or just very little or something that is totally wrong or doesn't perform well in the Q&A, then this may change. So make sure you split the time equally. And I've seen all strange explanations and excuses over the years, you know, like once someone did not attend and then he still wanted the same mark like the others because he claimed he created the slides, you know, and I did not clarify that you need to be present for a presentation. So it doesn't work this way. Or once a guy just kept presenting and after 8 minutes, and then when are the others presenting? And he just ignored me and kept talking. And then I said, when are the others? And he said, oh, we didn't know that the others need to present. And so, but if I try to write a rule book, I'll spend, you know, the whole term on just writing the rule book. Not too great. That's why I've emphasized the rules here. Any other questions? Yes? No, each topic can be picked only by one group. So that's why up to 4 people can join a slot in for, I don't know, pattern 5, and pattern 5 can only be presented once. Otherwise, you know, we have a lot of topics, and if we have 5 groups doing the same stuff, it's a bit boring. Yes? Somebody around really joins our group, you don't know about, like, you wouldn't want this. So please only join groups when you have discussed this with the others. Don't just, there's nothing I can really do to prevent this in the iLearn settings. I could only disable strange stuff that group members can rename groups or delete groups. You know, I've tried to turn this off. because of potential vandalism, but I'm unable to somehow control who joins the group and who doesn't. So please only join groups when you know those people and have discussed this. And sometime after April 30, 1 or 2 days later, I will upload a list in iLearn and notify you who is in which group. And please don't forget putting your student ID and all of this in the group description, because it's just lots of manual work trying to figure this out. And then you would check this list in early May, and in case there are any errors or whatever, we can correct it. Yeah. Yeah, but we're not done yet. Yeah. Okay. And next week, there's officially a lecture-free day, but we have just too many guest lectures this term because everyone wants to visit us and get to meet you and hire you. And that's why I also want to be able to finish with the content. So next week, Tuesday, we're doing this double lecture from 9 to 12. If you cannot attend, there will be a recording, but we're just being overrun by seminar by guest lectures. And there's a list in iLearn that you, so we have this lecture, this double lecture next week, and then we're done with the lectures and we only meet for these guest lectures. April 29, Tristan, maybe you know Tristan from LinkedIn. Anyone knows Tristan, the AI guru? Real brain and AI building models that generate music and arts. He will be here on April 29. May 13 is most likely online, and then May 20, we have 2 companies on site. And when they are on site, please come on site because it's an opportunity for you to meet them. Some of this is all varying. Christian was actually planning to be here on May 13 on campus. However, today in the morning, I received an invite for an event that I need to take on May 13th. So we'll do this online because May 3rd, on May 6th, we'll have a new chancellor. And I'm invited to an event with the chancellor on May 13 because they're now making all the plannings. And they sent this in the morning. So I will be at that conference in Berlin, but join in online with Christian. And who knows, maybe one company needs to reschedule and all of this. So we will see how this goes. But when I see the chancellor, I'll send you a photo through the course. And that's why also some company may need some other day because of a client meeting. So please keep an eye on this if it keeps changing, because we're still here for until end of June. Yes. Exactly. We don't have class when no of the guest lectures are scheduled because you also need some time to work on your seminar presentations. Good. And we still have a bit of time to continue with the content. So what we've seen so far is we've seen big data architectures to process big amounts of data. We've seen challenges when working with big data. Meanwhile, you should have also read the MLOps stuff briefly mentioned last week, which is helpful if you want to pick one of these design patterns in machine learning. So it's helpful to read the stuff in MLOps. And today we will look into uncertainty in learning. We'll see different models like Gaussian processes, conformal prediction, and others that help us to also quantify how certain or uncertain a machine learning model is. And we will also look very briefly at confidence intervals and statistical tests. So when you evaluate the predictions of a machine learning model, so the hypothesis, what you do is you have different sets of data, and you have a training set and a test set. If you want to compare multiple models, you would also have a validation set in between. We've already seen the issue of bias when these data sets come from different distributions. And when you have lots of different stuff you can pick to evaluate hypotheses. Say in classification, you have the confusion matrix. You can see per class which examples were or how many examples were predicted correctly and wrongly. And from the confusion matrix, you can calculate different metrics like accuracy, F1, precision, recall, R squared, or the area under the receiver operating curve. This one here is helpful. However, the AUC in the recent years has also got some criticism, some people claiming it doesn't work or doesn't provide much insights. It's still helpful for certain problems, especially when you have an imbalanced data set. The AUC can be quite helpful. You can do cross-validation. So there's lots of stuff you can do to evaluate your hypothesis. But there are challenges, class imbalance. If you have class imbalance, this severely impacts your accuracy. If you have other biases, whatever. So these are some issues you would face in classification. In regression, you face other problems. So R squared is a metric for regression. But in regression, you have the problem that every value you predict is wrong, because it will be hardly absolutely the correct continuous value that you wanted. So every prediction in a regression model will be more or less wrong to some extent. Doesn't sound great, right? If all your predictions are wrong. So with a classification model, that's maybe easier. And there are some interesting questions. For example, given the observed accuracy of a hypothesis over a limited sample of data, how well does this estimate its accuracy over additional examples? We always have a limited example on which we can train or test, but how would this actually generalize to more examples? If we have a hypothesis that outperforms another one over some sample of data, how likely is it that this hypothesis is more accurate in general? So one model is better than the other on one example or on one data set, but how does this generalize to every possible data set? And this should be actually data, not date. I always upload the slides at the end of the term when I fix some typos or something. So if you see any typos, let me know. And also when data is limited, what is the best way to use this data to both learn a hypothesis as well as estimate its accuracy? So maybe we have a limited amount of data. We want to use it all for training, but then we have nothing left for testing. How can we address this? In order to address all of these questions, we actually need confidence intervals as well as statistical tests. This is something you have seen in your statistics class. Who of you still feels comfortable with confidence intervals and statistical tests? Okay, one person. In particular, for this problem here in 2, to compare two models, how they overall work or outperform each other, what you need is usually a paired two-sample t-test. Anyone remembers the paired two-sample t-test? Remember t-test with the t-distribution, and the paired two-sample t-test is just a little bit more complex. That's what you actually need. I really like this stuff. And I wish I could teach it. Say, if I had the introduction to a machine learning class, this is the kind of stuff I would discuss, especially to solve these questions here. But I know this is not discussed in your intro to machine learning, right? These questions. It's actually something super important, and a lot of people don't teach it. And it turns out all of this was already published in the 90s. There's a super good machine learning book from the 90s. It's the Mitchell machine learning book, appeared in 97. It looks a bit outdated because obviously deep learning is not in there. There's something about neural networks and the world has changed. But there's some interesting stuff in there, especially chapter 5 is my favorite, evaluating hypothesis. This is something maybe you want to do during the Easter break if you have some time. Take a look at that chapter. It's a super phenomenal chapter and addresses all of these questions and also cover some of the maths you may need for a revision. Check if I have it here. Is it in the Nextcloud? Okay. And I'll just open it briefly. So it's not on my local storage, but if it's in Nextcloud, then you'll find it. Sorry? Okay. Don't have it on my local machine, but fine. Take a look at it. It's something that is super helpful and will help you to answer all of these questions, and you need, in order to answer them, confidence intervals and statistical tests. I wish it could be put in a machine learning class. So when I did my master's in machine learning, we discussed this in detail in one of the machine learning classes. And I think this kind of stuff is more important than just looking at the latest neural network or whatever in a machine learning course, because this is something that you need for your whole career. But it's, I think, how long is the chapter? I mean, 40, 50 pages. So yeah, whatever, just read it. It will provide you with some interesting insights. Now, we also want to know from a regression model how certain it is about its prediction. Because I said every regression model, eventually, every prediction it makes is wrong. And we want to know how bad is it. And one model that can do this for us by nature is a Gaussian process. What is a Gaussian process? Scikit-learn says Gaussian processes are non-parametric supervised learning methods that are used to solve regression and probabilistic classification problems. So the Gaussian process can be used for both regression as well as classification. And non-parametric, what does non-parametric mean? Anyone knows in the context of machine learning? Because there are parametric and non-parametric models. Parametric is something like linear regression or a neural network where the number of parameters is fixed. And non-parametric, very important, it doesn't mean you don't have parameters, but the number of parameters is not fixed. For example, a support vector machine is non-parametric because what it tries to find is the support vectors, and the number of support vectors may vary based on your data set. Wikipedia has a longer description of what a Gaussian process could be, but you can either read this or I'll show you what it is. This is an example from a regression problem. What we have is a very small sample of examples. We have these blue examples here, which are our observations. 1, 2, 3, 4, 5, 6. And what we have is these observations, they come from a function, which is x times sine x, this one here. And this function is plotted with these dots, blue dotted line. But we don't have the exact function, but rather we have observations with some noise. And these are these blue dots. And what I want to do now is I want to do a regression for this whole interval. So I want to estimate actually this function. And what I'm estimating is this orange line. This is what I can estimate with lots of models, maybe also with a linear regression that maps this into a higher dimensional space. But eventually, I just don't know how certain the model is. Like a linear regression can tell me nothing about its certainty when I use it to make a prediction. This Gaussian process, however, also returns me a 95% confidence interval for my function. And this is quite cool because I see if I make a prediction, so the prediction here would be, for example, for that x, the prediction would be here on this function on the orange line. But I just don't know with a regular model how good or bad is that prediction based on the data. And the Gaussian process tells me this by giving me the 95% confidence interval. Where I have enough samples, I have a very tight confidence interval. And out here, where I just have a lack of data, I get a very wide confidence interval because the model is just extremely uncertain. Something like this is really cool. And where do you need this? Say, if you make a prediction with a machine learning model, and the question is, will this lead to an automated decision or not? You know, will it reject someone's loan application, or will it decide about who survives in an autonomous car? Maybe you want to use a prediction made by a machine learning model if it's very, very certain about it. But if it's not very certain, maybe you want to use some other system, or you want to use human input to decide. So this kind of stuff is important also to increase acceptance in companies, because what they think is, oh, machine learning is like a black box. And even if you present them with, I don't know, explainable machine learning, they may still not trust it. But if the model can say something about its confidence, then that's quite helpful. So something you may need in a lot of real-world settings, in fact, and this is something that can be done by a Gaussian process. A Gaussian process is very interesting. We can use it to give reliable estimates of their own uncertainty. We can even incorporate expert knowledge using priors or so-called kernels. So kernels like in an SVM can also be used here. So this is quite interesting. But there are some disadvantages. The Gaussian processes are very computationally expensive because they're non-parametric. And they don't work very well in high-dimensional spaces, especially when we have a few dozens of features, which we have with a lot of real-world data. Then these Gaussian processes become super slow and they don't work too well because of the curse of dimensionality. But for some problems, they are super helpful. So this could be something you can easily use it in scikit-learn and train it, and you can get an estimate of their certainty. And you can also use it for classification. And now there is something else. And we'll start with it. We will not finish it today. But this is called something that has become super popular in the last few years in machine learning. It's called conformal prediction. Conformal prediction is, from its theory, relatively simple, where we still need some maths, but we can use conformal prediction and plug it on top of a lot of different machine learning models in order to do some kind of uncertainty or certainty estimation. It works different to a Gaussian process, but it's something that we can plug on top of on a lot of models. And what we have is, we want to create so-called prediction intervals or prediction sets. It's a frequentist approach, so not a Bayesian approach, a frequentist approach. So we want to have guaranteed frequentist coverage probability from any predictive method where the label depends on X. So not all machine learning models in supervised learning work this way. Some, they work in a different way. But if you say, I want to work with a method, the probability of a label given the data. And for this, I can always plug conformal prediction on top. The great thing is, a lot of machine learning methods that you use all day long, they always make an assumption about IID. Who remembers IID? Anyone remembers IID? IID is something we estimate about the errors in our machine learning model. With IID, so independently, I will look it up what IID means. With IID, because I want to put the two I's in the right order, so I also quickly need to up. Independent and identically distributed. That's what we assume about the errors in our model. So we assume that the errors follow a normal distribution. This is something we assume in a lot of machine learning models. And once our data doesn't follow that assumption, then it doesn't work well. And that's why there are all these tricks trying to tailor your data to some normal distribution and hoping it works better. I guess you've seen this. And IID is helpful, but from the methodology, it's from the last millennium. It's still important, and we need logistic and linear regression and neural networks, but a lot has happened in statistics since then. And conformal prediction is distribution free. So it does not make any assumption about the distribution of our data when we plug it on top of a model for conformal prediction. And this works overall very well. And it makes only a tiny assumption, which is exchangeability. And exchangeability means, in this case, the exchangeability assumption means that we can randomly change the order of our examples in the training set. This is something you can do with a regular supervised learning problem with static data. But if you have dynamic data, the data is not exchangeable because it's a time series. You cannot just randomly reorder the time series. So the only thing we require, there's no need about the distribution of the data or anything else. We only assume the data, the training data is possibly also the test data is exchangeable. So it's a very small assumption we're making. That's all we need. There are also extensions of conformal prediction to time series data, but this is not relevant for today. In the next lecture, we will discuss this conformal prediction approach and see how it allows us to do uncertainty quantification in a model, both for regression as well as classification. And there's a very good book that covers this now. So Murphy's probabilistic machine learning book is something that has been used by academia for decades as a machine learning reference. It's not my favorite one, but it's still a very helpful book. And Murphy, he released the probabilistic machine learning book now as two books 2 or 3 years ago. First, the first book, and then the second one, Advanced Topics. So these two books to cover also now much more than the old one book. And the Advanced Topic book covers conformal prediction on a few pages quite well. And next week, we will see how we can calculate a conformal score in a prediction model. And we will apply this to both classification and regression and see how we can actually estimate uncertainty in our model. And we will apply this also to some computer vision task and see how it works. And there's actually a library that we can use and plug on top of our existing models like scikit-learn, TensorFlow, PyTorch to do conformal prediction well. In the next lecture, we will finish this uncertainty in learning, and then we will also look, since it's a double lecture next week, into some recent questions, recent issues in NLP, as well as quantum computing. And then after the double lecture next week, we're done. Are there any questions from you about the content today? Yes? Yeah, because next week is a lecture-free day officially after the holiday, but I've sent the announcement that we are doing this double lecture from 9 to 12 because in the following weeks, everyone wants to come here for guest lectures. And we want to finish the content, and then you're also ready to have all the content to prepare for your seminar present. And for those who cannot join it, so it's only online, not on campus, but the ones who cannot join in on the Zoom session can watch the recording. All right, so there are no more questions, and I wish you a great few holidays on the weekend, and I'll see you then for the guest lecture on April 29 in 2 weeks from Tristan here on campus, and I expect you to be here. Take care.